welcome to your unit about dilations and similarity. You may have heard the word dilate when you come back from an eye doctor appointment. Your pupils might be dilated. Your pupils might look larger than they normally are because they had light shown in them. When someone's giving birth, a lot of times knowing when the baby's going to come depends on how much the cervix is being dilated. Again, dilation just means being enlarged or shrunk down. Let's look at one of Emma's favorite drinks as an example.
Let's take a look at this Dr. Pepper Zero can right here. As Tiana was saying, dilation refers to something getting bigger or something shrinking. So let's see if we can make this Dr. Pepper Zero can shrink. So if I pull this side in, what happens to my Dr. Pepper can? Well, it definitely shrunk, but it doesn't really look like a Dr. Pepper can anymore, okay? Let's try it this way. What if we want to shrink it this way? Again, it kind of distorts the image. And the same would happen if we made it larger, right? So one key thing that is true about all dilations is that each piece of whatever we're dilating has to grow by the same amount. So if we want to enlarge this image, if we pull down on the corner, then the image will get larger. Our height and our width of our soda can will grow at the same rate or change at the same rate. Same with if we shrink it. Now it's shrinking at the same rate, so it keeps the image the same as it was without distorting it. So the key with dilations is that everything has to change at the same rate.
All right, let's refine our definition of dilations looking at this graph here. We got triangle ABC, and then it was dilated at point A, so stretched from point A, and now we have triangle A prime, B prime, C prime. If you're unfamiliar with that little apostrophe, that means prime, and it is just a corresponding point after an image has gone through a transformation. So in this case, dilation. Just like Emma shared with us last time, the side lengths change, grow or shrink at the same rate. So if I look at AC here, AC is a distance of 1, 2, 3. So this is a side length of 3. And let's see if we can see how much it got dilated by. From A to C prime, that's a distance of 6. We went from 3 to 6. All right, let's look at BC. BC has a length of 4. And if we look at B prime, C prime, that has a length of 8. Something else I noticed about these triangles is that this is a right angle here. This is a right angle here. We can see that these are both right angles. So if I want to find the length of the hypotenuse here from A to B, I can use the Pythagorean Theorem, which states if I have side lengths AB and a hypotenuse of C, then A squared plus B squared will equal C squared. A way to visualize this is if I made a square off of A and a square off of length B, then those two areas added together equal the area of the square of C. In this case, we got 3 and 4. Those can be our A and B, and we don't know our hypotenuse. So we're going to say 3 squared plus 4 squared equals C squared. 3 squared is 9. 4 squared is 16. 25 equals C squared. Square root both sides to undo that square, and C equals 5. So we know that this length is 5, and hopefully we can see a pattern here. 3 to 6, 4 to 8. Maybe you're screaming at the computer now, it's just multiplied by 2. And so I don't have to go through the Pythagorean Theorem again with 6 squared and 8 squared. I mean, I could, but because I know that all the sides are multiplied by 2, then I know that this hypotenuse from A to B prime is also multiplied by 2. I know that is a length of 10. So we see that side lengths change or grow and shrink at the same rate. Another word for this is called proportional. A proportion is whenever two fractions are equal to each other. So I can make a fraction with 3 and 6, and that is going to be the same fraction as 4 and 8, and that's going to be the same as 5 and 10. The side lengths are what we call proportional. This number here too is called our scale factor. Because we multiplied all the sides by 2, we can say that triangle A prime, B prime, C prime is twice as big as triangle A, B, C. So you see, to get from the smaller triangle to the larger triangle, I have to multiply by 2. If I simplify each of my proportions down here though, I see that I get 1/2. And you can see here that this is the same as a 2 to 1 ratio or a 1 to 2. It just depends on which way you're going. So I could say that triangle ABC is half the size of triangle A prime, B prime, C prime, or the other way, A prime, B prime, C prime is twice as big, or 2/1, twice as big as triangle ABC. So there's a relationship here between the scale factor and the proportions. If I simplify down the proportions, I get the scale factor. You just have to remember which way you are going. Or if I'm going down, shrinking by 1/2, or am I enlarging, multiplying by 2? It just depends on which way you're looking at it.
So now that we have talked about what the side lengths look like when we dilate something, let's talk about what happens to the angles. So if we say that this angle right here on our paper is going to represent angle ABC, this little angle right here. If I line this up right here, let's see, how does angle ABC relate to angle A prime, B prime, C prime? How does it relate to this angle up here? So if I shift this up here, we can see that it matches. When a shape is dilated, the angles stay the same, or the angles are congruent. So no matter how big I stretch this small triangle right here, this ABC triangle, this angle will stay the same. So I stretched it by a scale factor of 2, and my angle doesn't double, but it stays the same. And we can see that as well here with our right angles. We have a right angle in our original small triangle, and then we enlarge the shape by a scale factor of 2, and we still have this right angle here. And then we come over to angle A and angle A prime. They are the exact same angle. They both share this piece right here. Even though the shape was enlarged, this angle stays the same. So side lengths have to grow or shrink at the same rate, and angles do not change. All right, let's look at these shapes right here. We have this little tiny C and then a C that has been enlarged. Let's see if we can figure out what the scale factor is when this shape is dilated here or when this shape was shrunken down to here. If we start with our smaller shape, side length 8 corresponds with side length 24. So I'm going to draw an arrow from 8 to 24 so that I know that 8 corresponds to 24. And if we look at side length 6, corresponds to side length 18. So I'll draw an arrow 6 to 18. So if I'm trying to figure out what my scale factor is, I can create a proportion. So I can say 8 over 24, if this shape is dilated, should be equal to 6 over 18. If I simplify 8 over 24, I'll get 1/3. And if I simplify 6 over 18, I will also get 1/3. So this 1/3 tells me that this smaller shape is 1/3 as big as this bigger shape up here. Or I can take this 1/3 and I can write the reciprocal. If you remember, the reciprocal of a fraction is the fraction inverted or flipped. So the reciprocal of 1/3 is 3 over 1. And this tells me that the bigger shape is 3 times as large as the smaller shape, because 3 over 1 is the same thing as 3.
All right, the cool thing about proportions is you could see it this way. 8 corresponds to 24 and 6 to 18, so you can correspond across shapes, but you could also correspond within shapes. What if I did 8 to 6 instead? If I correspond 8 to 6, or height within its base, then that would correspond to height within its base. So I could go from 24 to 18. So my proportion now could look like 8 over 6 equals 24 over 18. And we can see here, if I reduce this fraction down, 8 over 6 simplifies, I get 4/3. And if I simplify 24 over 18, if I divide both the top and bottom by 6, it's the same as 1. 24 divided by 6 is 4, and 18 divided by 6 is 3. If you don't like simplifying fractions by hand, you can also always type in your calculator and make sure that the decimals correspond exactly. So if I got the decimal versions of these, I would get 1.333 repeating, and that does indeed equal 1.33 repeating. So this doesn't give me the scale factor because it's not across the shapes like Emma showed us, but it does tell me that my height is 1 1/3 times bigger than its base, and height here is 1 1/3 times bigger than the base. So if you're trying to find the scale factor, try to go across the shapes. If you're just solving for missing sides, you can use either method, and we'll show you some more examples.
Let's look at these shapes right here and see if we can figure out what this side length is here. This is labeled as X, and so we want to see if we can use the idea of scale factor to figure out what this missing side is. So let's look at what we do know. We do know that this side length 6 and this side length is 72. So we're trying to figure out what times 6 is going to give me 72. What do I have to multiply this 6 by? Give me 72. You can use a calculator. You can say, well, 72 divided by 6 equals 12. So that tells me that I have to multiply 6 by 12 in order to get 72. Or if you just know that off the top of your head, that's awesome. So if we know that I have to multiply 6 by 12 to get 72, that means I have to take my 8 and I have to multiply that by 12, because we know that side lengths have to grow or shrink by the same amount. And so 8 times 12 gives me 96. Again, you can do that in your calculator, or if you just know off the top of your head, that's great. So we have 8 times 12 gives me 96. So I know that my missing side, X, 96. A common misconception with dilations is if we look at a side length that we know and we're trying to figure out, well, how did 6 get to 72? We can see it's multiplied by 12, but another way 6 gets to 72 is if you add 66. If I added 66 to 6 to get 72, that means I have to add 66 to 8, and that should give me 96. But 8 plus 66 gives me 74. So that is not 96. So when we are working with dilations and scale factors, when it says grows or shrinks by the same rate, that's talking about multiplication, not addition. So make sure when you're seeing, well, how does 6 get to 72? You're trying to figure out, what do I have to multiply 6 by to get 72? Or what do I have to multiply 8 by to get 96?
All right, let's check out this Desmos activity to further solidify the relationship in scale factors. So here we got this nice polygon here, this quadrilateral with 4 sides, and our scale factor is set at 1. What happens if we move our scale factor to be larger than 1? All right, we see that our dilated image gets larger and larger, right? Which makes sense. If I make it 5 times big, it's going to be much bigger, right? Versus 2.5 2.6 times big, 2.3 times. So when it's exactly 1 though, we would say that these figures are congruent. The blue and the red are right on top of each other. So when we have a scale factor of 1, that means they are congruent. If we go smaller than 1, scale factor of 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, we see that it shrinks. And so a scale factor less than 1 shrinks our figure. Scale factor equal to 1 is congruent, and a scale factor bigger than 1 will give us a larger shape. All right, just to recap our scale factor, if our scale factor is 1, then that means the resulting shape and the original are congruent. If our scale factor is less than 1, then that means our resulting image is smaller or shrunk down from our original size. And if it's greater than 1, that means our resulting shape enlarged or is bigger than our original shape.
Okay, let's take a look at these two shapes up here. This blue shape is our original shape. It's A, B, C, D. And this orange shape is our resulting image after it's been dilated. It's A prime, B prime, C prime, D prime. So that's what's labeled here. And so if we look over here, we know that our scale factor has to be less than 1 because our original image shrunk down to our resulting image. So if we look at the side lengths of this rectangle here, from A to B, this is a side length of 8. And from B to C, this is a side length of 4. And then A prime to B prime is a side length of 6. And B prime to C prime is a side length of 3. If we want to figure out what the scale factor is to get A, B, C, D to A prime, B prime, C prime, D prime, then we have to take the side lengths of our dilated shape and divide them by the original side lengths, and that will tell us what we had to multiply this large shape by to get the smaller shape. So we'll say 6 over 8 because 6 and 8 correspond with each other, and then 3 corresponds with 4. So I will say is equal to 3 over 4. If this is a true dilation, these two fractions should be equal. They should be proportional to each other. So if we simplify 6 over 8, then we get 3 over 4, which is equal to 3 over 4. So this number here, this 3/4, tells me that I have to multiply everything in this original shape, A, B, C, D, by 3 over 4 to get the A prime, B prime, C prime, D prime shape. And we can test it out to make sure that's true. So if I take 8 and I multiply that by 3 over 4, we know that when we multiply by a fraction, we can just put this over 1 to make it a little bit easier. So 8 times 3 is going to give me 24. 4 times 1 gives me 4. 24 divided by 4 is equal to 6. So that's perfect, because that's this side length here. And then if we try that with the 4 and the 3, well, 4 over 1 times 3/4 is going to give me 12 over 4, which is equal to 3, which is this 3 right here. So my scale factor is less than 1 because my original image shrunk down when we dilated it. So I have to multiply 8 by 3/4 and 4 by 3/4 to get my resulting 6 and 3 side lengths.
All right, so Emma just shared with us that our scale factor from shape ABCD down to A prime, B prime, C prime, D prime is 3/4. Now we're going to talk about how does the scale factor affect our perimeter and our area. If you remember the perimeter of a shape, the perimeter means it is the outside edges. So if I were to build a fence around this polygon here, I want to know how long is it. So it's 8 up here, 4 here. Since it's a rectangle, we know it's going to be 4 over here and 8 over here. 8 plus 4 plus 4 gives us 24. So we would say the perimeter for ABCD, which I'm going to actually write as a subscript here so we remember which one it is equal to 24 units. All right, let's check out the perimeter of our resulting shape. We got 6, 3, again rectangle. This has got to be 3 and this has got to be 6. And so we got 6 plus 3 plus 6 plus 3. So we can say that the perimeter of A prime, B prime, C prime, D prime is equal to 18 units. All right, is there a relationship going on between 18 and 24 and our scale factor? Because we know within the sides it was scaled by 3/4, we can say that the whole perimeter is scaled by 3/4. So let's check that out. If we got 24 units and we times that by our scale factor of 3/4, 24 times 3 gives us 72. And again, this is like 24 over 1. 1 times 4 gives us 4. 72 over 4 is the same as 18. So we see that when we have a scale factor of 3/4, then our perimeter is also multiplied by that scale factor. So that's a nice shortcut. If I have a weird scale factor and I have to find the perimeter of a resulting shape, I can just use the scale factor between the sides to figure out the perimeter of the resulting shape as a whole. We see here that our scale factor is 3/4, so that means that my perimeter here is multiplied by 3/4, and that gives me my perimeter for this shape. If I had a different example where I had a shape here and the scale factor was 1/2, the perimeter here would be half the size of this perimeter here. Let's look at the area between the shapes and see if we can find a relationship with our scale factor. So remember, the area is all the space within a shape. So when we have a grid, it's really nice because we can just count up the squares here and just count up each individual square here and each individual square here as well. Or you can also use your area formulas to help you. We have a length of 8 here and a width of 4 here. 8 times 4 is 32 units. units, and because we're talking about the squared area, we're going to use a little 2 units squared. All right, let's see if we can find the area of this one. 6 times 3 gives us 18, or there's 18 little squares inside here. So the area of A prime, B prime, C prime, D prime is 18 units squared. Right off the bat, it's probably not easy to tell maybe a relationship between 18 and 32. We saw with the perimeter that if I multiplied it by the scale factor, it gave me the new perimeter. So let's try multiplying 32 by our scale factor and see if we get 18. 32 times 3/4, which is the same as 32 over 1. 32 times 3 is 96 divided by 4, 24. All right, and we see here that 24 is not the same as 18. All right, so we saw that multiplying by the scale factor once didn't quite work. But remember with area that it's squared. So that means we're not just talking about one dimension, but 2 dimensions. So we need to actually try multiplying by our scale factor twice. So what happens if I multiply 32, not just by the scale factor once, but by it 2 times? I can put 32 over 1. 32 times 3 times 3 is 288, divided by 1 times 4 times 4 is 16, and 288 divided by 16 is 18. So we see that these do match up. So our shortcut for our area is if I have the area of some shape and my shape gets dilated by a scale factor, then the resulting area is going to be multiplied by that scale factor squared. 3/4 times 3/4 is the same as 3/4 squared. So our pattern for our area is that the area for our original shape is multiplied by the scale factor squared to get our resulting shape's area. So scale factor is 3/4, so my perimeter changed by 3/4, but my area changes by 3/4 squared.
All right, let's take a look at this image here and see if we can just figure out what the area and the perimeter of this image is. So perimeter is pretty simple. We are just going to take the side lengths of this quadrilateral and add them all together. So 3 plus 5 gives us 8, plus 6 is 14, plus 4 is 18. So our perimeter is 18 units. All right, now let's see if we can figure out what the area is. In order to figure out the area of this shape, we're going to have to break it up into 2 different shapes. So let's draw a line here. So we now have a triangle and a rectangle. So the area of a rectangle is pretty simple. We can just see that the length times the width, 4 times 3 will be 12. So the area of this piece is 12, and now we just have to find the area of this part. If we can see that this part of our rectangle is 3, that means this part will be 3. And if the whole thing is 6, that means this remaining part here is going to be 3. We can say that this part of our triangle is 3, and we know that the height here of our triangle is 4, because that matches up with this side here. So the height of our triangle is 4. And the area of a triangle comes from our base times our height divided by 2. So 3 times 4 is 12, divided by 2 is going to give me 6. So the area of this here is 6 units squared, and this is 12 units squared. So if we have 12 plus 6 gives me 18 units squared.
All right, now that we have the perimeter and area of our original shape, let's see if we can find the perimeter and area when we take this and we make it twice as big. So we are dilating this by 2. So we know since we are making it twice as big, our scale factor is 2. Now I could redraw this. Instead of 6, I know it's twice as big as 12. Instead of 5, I know it's twice as big, which is 10. Instead of 3, it's twice as big, which is 6. Instead of 4, it's 8. And I could add and find my perimeter this way, and also I could find my area this way. However, I can use the properties I know about perimeter and area to make this go by faster. So because I know my perimeter, my original perimeter is 18, that means I can just multiply it by my scale factor to get my new perimeter. So 18 times 2, because it's twice as big, it's going to give me 36. So I know my perimeter of my new shape is 36 units. Let's look at the area. Again, I could chop this up and do what Emma did here, where I find the area of this rectangle and find the area of this triangle and then add them together. Or I could use the property found, which is that the area of the original shape is multiplied by the scale factor squared to get the area of my new shape. So my original area is 18. So if I do 18 times my scale factor squared, that's going to give me my new area of my new shape. So 18 times 2 squared, which is 18 times 4, is the same as 72. So I know that my area here is 72 units squared. And you can verify that over here. 8 times 6 is 48. And then this is a height of 8 and a length of 6. This would make a rectangle. 48 cut it in half would give us 24. And so 48 plus 24 does give me 72. So you could verify it this way as well. But this just shows that our shortcut for finding the area and for finding the perimeter when given the scale factor works.